Real quick, I wanted to go over how HTTPS works. So in our web browsers today, when you go to a website, typically you're using HTTPS to transmit data that's encrypted. Chrome hides that. They don't want to show you all that protocol information, but it's there. If you look for it, we're using HTTPS. If you're not using HTTPS, you're using regular HTTP, and it will say something like not secure. I really don't like that, to be honest. Just because something is HTTPS doesn't mean it's secure. It just means it's encrypted. A scammer can set up a website to steal your credit card information. And as long as they are using encryption, your web browser might tell you, yeah, this site is secure, and I don't like that. It just means it's encrypted. The connection is encrypted between you and that web server. So in the olden days, we used the RSA key exchange. So if I want to send data to the server jimmarkwardson.com, I'm in my home. This server is in a data center somewhere. So we have to exchange a key, a symmetric key. But how do I send that symmetric key? If I send that symmetric key unencrypted, anybody could eavesdrop, theoretically, grab that key, and then they can decrypt all of our communications. Well, that's no good. So the RSA key exchange, it uses the RSA crypto system. It uses certificates. So if I go to jimmarkwardson.com, there is a certificate there. So I'm in the Chrome developer tools here. You can find them Control-Shift-I or more tools, developer tools. I'm on the security tab now. There's a bunch of different tabs. I'm on the security tab. It's a little squished because I've got two windows side by side here. But I can view the certificate if I want to. So Let's Encrypt, they gave me my certificate. My service provider set all this up for me. But we can see in here, there's subject's public key, my public key. I've got a public key out there. For my website, there's my public key, just a bunch of data. Anyway, if we were using the RSA key exchange, me in Marquette, I could encrypt a temporary ephemeral symmetric key using this public key. Now, who could decrypt that? Only the server that has the private key could decrypt that information. So if I encrypt something with a public key, I send it over the internet. Nobody can get that and decrypt it because they don't have the private key. Only the server that's got the private key associated with that public key can decrypt it. So once they receive it, they decrypt it. Now I know the temporary ephemeral key to use for symmetric encryption. The server knows the temporary ephemeral key for encryption. And then we will start transmitting data using symmetric encryption. We're probably, in 99.9% of cases, going to use the AES symmetric encryption algorithm to send and decrypt that data. It's much faster, much more efficient for sending large amounts of data. So we're really only using asymmetric encryption to bootstrap the process. Then we're using symmetric encryption to actually transmit all of this page data here. So does HTTPS use asymmetric or symmetric encryption? The answer is yes, it's actually both of them. Now the RSA process works. There's a downside though. What if the server, somebody hacks into it, somebody gets access to it, and somebody steals that private key? Well, that means all of those temporary keys could be suspect. Somebody could decrypt that data. So that's not good. So this does not provide perfect forward secrecy. So transport layer security version 1.2, which was used for a very long time, allowed this RSA key exchange. In TLS 1.3, which is what's commonly used today, we don't use this same process. Notice if I look, it says my connection is secure, TLS 1.3 X25519. We're using elliptic curve cryptography to exchange temporary keys. And then notice it says and AES 128 GCM. So once we exchange those keys, we are going to use the AES algorithm with 128-bit keys using the Galois counter mode, that specific block mode of operation, but that's going a little bit deeper than we need to be. So this is different. When I establish a secure connection using TLS 1.3, my browser generates an elliptic curve key pair. I send it to the server and I'm like, hey, let's create a secure channel for communication. The server creates a new key pair also, so on the fly. It's a pretty cheap operation computationally. We're just picking random numbers and finding the public key. It's not that difficult. So we both create brand new key pairs, public key, private key, key pairs, and we send each other those public keys. And then there's a little bit of math we have to do. We essentially multiply our private key with their public key. We both do that same thing. Google multiplies its private key times my public key. I do the same thing. I multiply my private key times Google's public key. And the way this works, we end up at the exact same location on that elliptic curve, and that point on the curve becomes our shared ephemeral, that temporary key that we are going to use with symmetric encryption later on to actually transmit page data. So why is this better? It's better because let's say somebody somehow stole that key, the private key that I created. That key would only be used for my temporary communication with Google that one time. If I go to Google later in the day, or you go to Google, a million people go to Google, there's a million different private keys used. So it doesn't matter that much if, one key was tampered. You're not going to essentially undermine all of the security of all the other data that was encrypted on that server. So this provides perfect forward secrecy. This is better. It's the way that all key exchange processes are going for lots of different products, because people now trust elliptic curve cryptography pretty well. There was a time when people trusted RSA and they weren't quite sure about elliptic curve cryptography. The math has been well vetted, it's well understood, and it's kind of the way forward that a lot of products are moving for asymmetric cryptography.